So we want to find the zeros of this polynomial function. We know it's degree 4, so we expect to have 4 zeros. However, this is definitely not a polynomial that factors easily using traditional factoring methods, so we will use our rational zeros theorem. So start by writing the factors of the constant term, all divided by the factors of the leading coefficient, and make a list of your possible rational zeros. So all the factors of 36, and there's quite a few, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, 18, and 36. Long list. All divided by the factors of 2, which would be plus or minus 1 and plus or minus 2. So the list of possible rational zeros for this function is quite long. We would have plus or minus 1, 2, 3, 4, 5, 6, 9, 12, 18, 36. And then also all those numbers divided by 2, which would create a bunch of fractions. So if you did want to list them all out, it would be lengthy. So it would include all the numbers in the numerator, and then if we divide by 2, we would have additional fractions like 1/2. 2 over 2 we already have because that's equivalent to 1. We would have 3 over 2. 4 over 2 we already have. 6 over 2 we already have. 9 over 2 we would add to our list, 9/2. 12 over 2 we have, that's 6. 18 over 2 we have, that's 9, and 36 over 2 we have as well. So this is our list of possible rational zeros. So now we're going to start our synthetic division. And if we're trying to do this one without a calculator, then you could do your synthetic division on a piece of scratch paper until you find one that works. Otherwise, you'd be doing quite a bit of erasing. So let's try 1. Does 1 work? Remember that if you're missing any terms, you want to be sure to include placeholders. So we want to include zeros for any missing terms in your synthetic division. So pause the recording and try 1 and see if it works. So after doing your synthetic division, you should see that 1 is not a 0. So we'll start over and we'll try -1 next. And it looks like -1 does work. So now we look at this row of values. The original function was raised to the 4th power, so these are going to be my coefficients of a polynomial raised to the 3rd power, 2x cubed plus 5x squared minus 21x minus 36. Now we set this equal to 0 and solve in hopes of getting our 3 remaining zeros. However, this does not factor, so we're back to doing our synthetic division again. So rather than using the original coefficients, we'll go ahead and stack our synthetic division and use the values 2, 5, -21, and -36. So notice that in this cubic equation, the constant is still 36 and the leading coefficient is still 2. So our list of possible rational zeros has not changed. So we've tried 1 and it didn't work. Then we tried -1 and it did. So now going through our list, so 2 would be the next logical choice. So pause the recording, try 2, and see if it works. So after doing synthetic division with 2, it does not work. The remainder is not 0. So next I would try -2. So same thing. Pause, try it on your own, see if -2 works. So after trying synthetic division with -2, we don't get a remainder of 0 either. So -2 doesn't work. Next number on the list is 3. Try synthetic division with 3 next. finally, you should have another 0. It looks like 3 does work. The remainder is 0. So right now we have 2 of the 4 zeros. And looking at this row in synthetic division, we have 2x squared plus 11x plus 12. And now we'll set that equal to 0 and solve. Now, the good news is when you get down to a quadratic equation, there's no need to do any more synthetic division because we can solve all quadratic equations. Either try to factor it, complete the square, or use the quadratic formula, whichever you prefer. And I believe if you try this one out, it does end up factoring. 2x times x will equal 2x squared. And if we choose a positive 3 and a positive 4, then the outside will give us 8x and the inside will give us 3x, which indeed will add to 11x. So this quadratic does factor. 2x plus 3 times x plus 4. So now we set each factor equal to 0 and solve. And we get our 2 additional zeros, negative 3 halves, as well as negative 4, both of which happen to be rational numbers and were on our original list of possible rational zeros. So we have our 4 zeros. So our zeros are negative 4, negative 3 halves, negative 1, and 3. And last we want to write this function in factored form. So our 0 of negative 4 came from the factor of x plus 4. Our 0 of negative 3 halves came from our factor of x plus 3 halves. Negative 1 came from x plus 1. And finally, 3 came from x minus 3. Now the only thing left here to consider is when you look at the leading coefficient in each of these binomials, they're all a 1. So if you were to multiply x times x times x times x, you would get x to the 4th rather than our leading coefficient in the polynomial, which is a 2. So to rectify this, we need to include the leading coefficient of a 2 out in front. This is one way to write your answer. There's a second way if you prefer. Instead of putting the 2 out in front, you could think of it as distributing. If you distributed the 2 into the factor that contains the fraction, so distributing the 2 into the x plus 3 halves, that is going to give us the factor 2x plus 3. And if you look earlier in your work, when we had factored the quadratic, indeed, 2x plus 3 had been the factor that gave us the answer of negative 3 halves. So if you would rather, you can write your factored form this way. X plus 4 times 2x plus 3 times x plus 1 times x minus 3. There's no need to have a number out in front because if you take a look at all of your first terms in these binomials and think about if you had multiplied this out, we would end up with a 2x to the 4th power.